Okay, so what is this test? Now, I would advise you to watch this video. The link is available on the frequently asked questions. Also in this PDF, if you click on this blue text, you will be taken to this video. Now, it's a seminar, around 90 minutes. It's long, but it's fun to watch. I mean, I really suggest you to look at it. Now, one of the things that I learned in this video about the lecturing. Okay, this is a quote that he quotes from one of his friends. I don't remember the name now. Now, traditional lecturing is nothing but the transfer of lecture notes from the notes of the lecturer to the notes of the student without passing through the brains of neither. So, what goes on in a lecture? There you have the lecturer. In the first hour, at least, I was lecturing. I was speaking for an hour, and you were just listening. Only towards the end of the lecture, some of you actually participated in the lecture. And some of you were just taking notes, and I see that some of you have problems in English, so the question is, how much do you understand the lecture? So the studies show that, in fact, the students don't really learn a lot in the lecture. So there have been some tests like this exam, which show that, I mean, you spend like 3 months in this class in the first semester. So 14 weeks, 5 hours every week, that makes like 90 hours in this class. And at the end, what happens is you just, among all the topics that we will cover, you will learn only 22% of the things that we have been discussing, on the average. I would say that's a waste of time. You are spending like 90 hours here listening. I will be spending like 90 hours of my time lecturing, and at the end, you only learn 1/5 of the things that you don't know. Now, there are ways to increase that one. I mean, in the video, he just promotes one of them at least. It's basically based on making the students, forcing the students, in a sense, participate in the lecture. And if the students participate in the lecture, that number can go up to 44%. Now, my experience, I have been teaching 2 years. I have been teaching this course for the last 2 years. In the first year, I was forcing the students to participate more in the classroom. I will be telling you how I did that. We have an SMS system here, a clicker-like system. I was using that system, and at the end, the students just learned around 41-42%, measured by these tests that we will be doing this year. And that's, I mean, for me, on my behalf, I would take that to be a success. Last year, though, I was kind of lazy. There were some problems in this SMS system that I used, so I didn't use it that much. The number, I mean, I was teaching the same material in the same way, except on this clicker system, and this number just dropped to 21%. So, at least in my case, I have a strong belief that if you participate, you can learn much more than if you don't participate, if you just listen to the class. So, and if you want to waste your time, you can just come to the class, listen passively without actively participating, and then you will be just wasting your time. Now, of course, one problem is what is learning. Now, let's start with some definition. What's lecturing? I mean, one of the things that you have to pay attention to in this year is to make a precise definition of the concepts that we are using in physics. Like, one of the most confusing concepts, it seems that you have a hard time understanding the concept of force, for example. Now, most of your questions or the things that appear puzzling to you when I discuss with students, I just ask them to define what they mean. And once they define what they mean properly, well, they don't have any questions left. So that is one thing we have to pay attention. Define everything that we are talking about. So we are talking about the lectures. What do we mean by lecture and lesson? These are the definitions, the ancient definition, the first use of these words. And lecture, action of reading. And the lesson, a reading aloud from the Bible. If you look at the etymological origins of the words, these are the definitions that you come up with. And that is still what we do. I mean, there is the professor standing in front of the classroom, he is lecturing, and the lectures are supposed to be from the book. So we are nothing but making a summary of the book, and you are just taking notes. Well, that was how people, at least in the 14th century, that was how people reproduced books before the invention of the printing machine, stamping machines. Well, that was the only way that you could distribute information. But nowadays it doesn't really make too much sense, because the information now, I'm sure most of you have many books in their pockets, in their smartphones. So what's the point in reproducing information in the lecture now? So when do you learn something? When do you say that, okay, I have learned this subject? Okay, don't cheat. Don't look at there.
When I can explain it simply.
You can?
When I can explain it simply. So
Okay. When he can explain it simply?
I can use for something or some aim.
Okay, use it for something else.
But I can explain to somebody else.
When you can explain it to somebody else. Okay, you can solve a question on yourself, on your own.
When things start to make sense.
Okay, when things, okay, I would understand that, but what does it precisely mean?
For example, before the class, I wouldn't know why this broke down.
Okay. Okay, so why questions? I will come to that why questions in a moment. Okay, now those are all great definitions. For example, my definition is, now if there is a derivation, can I do it without looking at the book? Can I reproduce the same reasoning? Repeat the reasoning. So this is mainly the why thing. Can I explain why I do each step? And of course, this is not about memorizing formulas. From time to time, I have some visitors from education departments or even English departments. They just wanted to know how much English do our students need to know. And they were quite surprised that we were talking so much, because their understanding, even the understanding of most students, is that physics is just a series of formulas. That cannot be farther from the truth. Okay, of course, one thing you have to pay attention to is that not all answers are always answers. What I mean is that, for example, this is a typical question that I like. Why are the leaves green? Because of chlorophyll.
Because it can absorb every other light.
Except on green light. Other answers?
because our eyes see green.
Because?
Our eyes see green.
Okay.
All colors except the green one are broken.
Okay. Okay, because they reflect green light, this was like half of the answers I got. But this is not an answer. This is just a rephrasing of the question. Why do leaves reflect the green light? Well, we already had, one of our friends had the answer, because they contain chlorophyll. Again, this is not an answer. This is just at least for a physicist, this is not an answer. This can be an answer for a biologist, which studies biological structures. And for them, chlorophyll is a fundamental biological structure. But for a physicist, it's just a rephrasing of the question. Why do chlorophyll reflect the green light? What's the green? Okay, so I can rephrase the question. Why do chlorophyll reflect the electromagnetic radiation of a given frequency?
It's just the way that it works.
Sorry?
It's just the way that it works.
Why?
It's just the way that it works.
Well, that is what we are looking for, the answer to these why questions.
Because the energy difference between it's just...
Okay, I mean, we know the answer to this question. We know a precise answer to this question, but we will not be discussing this. But the important point is, not all answers are answers. They just pretend to be answers, but they are not.
Is there any answer to any question?
Do we have a full answer to any question? Well, that is what, for example, CERN is trying to find out. What is the fundamental reason behind everything, let's say? Fundamental laws. Now the questions, the why questions. Okay, we have the what questions, the when questions, how questions, why questions. Now what the when you are asked what questions, for example, we will be discussing the projectile motion, we say, okay, what is the distance that it will fall? Okay, that's the what question. Or when will it reach the highest point? Okay, these type of questions you will get in the homeworks, you will get in the exams, even in this course. And if you can answer these questions, you will be getting high grades. But they won't really make you a physicist. And if you want to be a physicist, you have to pay attention to the why questions. And not all the why questions will have answers because we don't know them yet. But at least we want to reduce the number of different why questions we have to as little as possible. If possible, we want to reduce all the questions to one question only. So that if we make an assumption about that one question, if we fix the answer to that question, we will be answering all our questions. Now, one of the conversations that I have with my students, especially you have the midterm, then you come to my office to look at your midterm, how you solve that, from which points you lost the points. And then, okay, so this is the question, and you can just think of this question as the question in the midterm, and then your answer is the answer in your answer sheet. So then I ask the students the question, okay, why did you do this calculation? Now, the answer I quite often receive is that we solved a similar question in the class like that. Then I ask, okay, why still? I mean, that's not an answer to my question. Why did we solve it like that? And the reply is it wrong? So it's not necessarily wrong, but I still want to know why. Do you understand why we are doing that? Why we are doing such a calculation? And after that point, there's no answer. Because most of you are so much concentrated on learning the necessary steps to solve a given particular type of question, you don't really think about whys. Okay, you just, when you listen to the lecture also, that's what you want to grasp. When I solve simple questions in the class, I see all the students quite heavily writing down the steps. But when I'm talking to them, they start sleeping. Because it's boring, I mean, the talking thing, it doesn't explain them how to solve the sample questions. But that is what teaches you the whys, all the discussions about the formulas we have. Okay, the sources that will help you learn. The first one is not your professor. The first one is yourself. Now, okay, you know when you learn something, okay? One of you have said that, okay, by solving questions, you can tell whether you have learned it or not. But the problem with solving questions is that there are many cases in which the students can solve all the difficult questions, but when it comes to understanding, when it comes to discussing the concepts or explaining the concepts to somebody else, they don't understand it. We have all these students that get high grades, but when you start discussing with them, they cannot explain it because they have learned there's some typical questions and they can answer them perfectly without understanding why they are doing that. But you can judge on your own whether you have learned it or not. Now, how can you learn it by your own? Well, go to the library, pick up a book, repeat our discussion. So if you have solved the question but you feel that you didn't really understand it, repeat the subject, ask somebody else. And of course, your friends. Now, one problem with discussing with your professors would be that I have been in your chairs like 20 years ago. Now, after 20 years, I practically don't have any clue why you don't understand certain concepts that are so obvious to me. But your friend already knows it. What are the difficulties? What are the difficulties that you are facing? So if your friend has understood it, then it's more probable that he will be able to convince you, he will be able to explain it to you better than I do. So basically what I do is I just explain it the best way I know. But if you cannot understand it, then there is nothing much I can do about that. Because my explanation will be just a repetition of what I had said in the class, which didn't help you. But your friend can come up with a better explanation than I did. And then, if nothing works, of course, your professors, the library, and the books. Now, the learning thing. Now, you have to participate. But of course, with the number of registered students to this course is 170. Now, today there are like, at least when you were taking the exam, there were around 120 students, and that will probably be the typical number in the classroom. Now, if you all speak, and if you all take like 1 minute, that takes 2 hours. So, I mean, on one hand, you have to participate in the class, but if all of you participate, we will not be able to do anything. But there are other ways of making you participate. This is the SMS system that I was mentioning about, the one that I intend to use this year. So let's give it a try. Okay, so here is the question we have. Okay, so you have this phone number, 4660. You can just send SMS messages to that number free of charge. And, well, this is the question and some possible answers. So let's give it a try. Okay. You can just send your SMS. Now, during the course, for actual physics-related questions, the way it will work is I will just put up a question, and then you can just send your answers through SMS. And once you send your answers, I want you to discuss with your friends, with your neighbors, and just make sure that all your neighbors agree with you. You can change your mind. Why not? Well, 43 people managed to send them, so I will just treat you as measurement error. Well, typically half of the students send SMS. So almost everybody who sent the SMS managed to send them. So at least that tells me that it's not a problem with the system. It's probably you have a problem with your phones.
More than one?
No. You can only send one answer. If you send it a second time, you might have already sent it without knowing it, because it will not accept your second answer. I have no access to who sends which answer, by the way. So it's completely anonymous. Okay, so there are some answer A's. Just make sure that the next time you go to the correct class. Okay, this is how it will work. Well, of course it takes time. I mean, okay, 5 minutes for your answers to send and for your discussions. After the 5 minutes, we will discuss the answers. In this case, for example, there are 2 dominant answers. I just would like those 2 groups to convince each other. So it's not just 5 minutes sending the reply. When this C group and D group, they will be discussing with each other, trying to convince each other. Now, it takes time, but I think it's worth the effort. I mean, in 1 hour, most of the time we can discuss at most 4 questions. But I will spare at least 1 hour during the week for these discussions. Okay, so this is how it will work until the 5th minute. Okay, that's terminated. Okay, this is how I see it. Physics is everything around you. So quite often students come to me asking, oh, do you have some sample questions? Well, the questions is all around you. Just look around. Can you explain them? Can you explain all the phenomena that you see around you? Now, one drawback about this one is I also had students who were saying, oh, we don't know enough to explain everything around us. But think like this, Newton knew less than you did. Now, probably you already know more than what Newton knew at that time. I don't think that prevented Newton from asking questions and trying to understand the nature. Now, physics is about doing scientific research, let's say, is about trying to explain what you see around you with the things that you already know. And if they are not, only if they are not enough, if you have enough evidence that they are not enough, you try to develop new methods. And of course, the measurement is most of our definitions will be somewhat related with measurement. Without measurement, physics doesn't have any meaning. And if you cannot measure something, that's no longer physics. I mean, of course, this measurement, it might be that we might not be able to, technologically, we might not be able to measure something right now, but that doesn't mean that we will not be able to measure it, I don't know, in 20 years, 30 years, in the next 1,000 years. Even if there is a slight possibility that something can, in principle, be measured, then it's part of physics. If it cannot be measured, then that's no longer physics. And the measurements, it's important that people should be able to repeat the measurements. This is especially important for labs, for example. You will be doing experiments. And if somebody else wants to repeat your experiment, they have to be able to do it, given they have enough equipment. So you have to keep precise note about what you have done. You have to be able to explain that. If you just say that, okay, I measured the thing and I found 500 something, that doesn't mean anything unless you tell somebody else how to do the same measurement. And of course, every measurement has units and every measurement has errors. The error bars are crucial. For example, if you measure a distance, we will be talking about distances. If you measure a distance, let's say 3 meters, somebody else measures the same distance 4 meters. So are they wrong? Can they both be correct?
Yes.
They can be correct if you take into account the errors. For example, it might be that your measurement has plus minus 1 meter error. So in such a case, although one person measured it 3 meters, the other one measured it 4 meters, they are consistent with each other within their, what we call the error bars. Now, units are also an important part of your physics expression, whether they are measurements or whether they are formulas. Now, 1 meter and 1 millimeter is definitely quite different from each other. Now, one problem that, especially the new students, your habits from high school teach you that if you are given a problem with numbers, you just ignore the units. Now, that is wrong. Keep the units. You should keep the units at all your stages. If you put 1 in your expression, that is wrong. Is it 1 meter? Is it 1 second? Well, sometimes the students say, oh, it's obvious from the question that it is 1 meter, so there's no 1 second. But, okay, especially if you teach somebody or when you start preparing exams for 100 students, you start to realize that a question or an expression that is so clear to you can have 100 different interpretations. So just to avoid that, you have to keep your units. If you are doing a calculation, you always have to keep your units at every step of your calculation. And the units are also nice because they allow you to check for errors. For example, if you are required to calculate some velocity, and if you find that the final expression you obtain is 5 meters, then you definitely know that what you have done is wrong. You have to have made some mistake somewhere during your calculation because the velocity should have the units meters per second. It cannot be meters. Okay, some of the students just add meters per second at the end. But that just doesn't help you. Okay, in measurements, there are these two related but not the same concept. One is the precision, one is the accuracy. Now, precision, what we mean by precision is that suppose you make 100 measurements. In all the measurements, do you get the same number or different number? You might be getting different numbers. In fact, in all the measurements, every time you measure, you get a different number. That will determine the precision of your measurement. For example, if you are measuring a distance, if you use a ruler, your hand just might slip very slightly. So you might measure the same distance 1 millimeter larger. Or you might be, I don't know, rather than looking from the straight up, you might look from the side. That would change your measurements slightly. And all these contribute to the precision of your measurement. It's easy to determine the precision of your measurements by just repeating the measurement over and over again. If you get the numbers that you will get, they will have a spread, and the spread will tell you what is the precision of your measurement. And that the precision will contribute to the errors. Now, the more problematic one is the accuracy. Now, accuracy just means how close is your measurement to the real value. So what is the real value? How do you know the real value?
From textbook.
Okay, so let's imagine we are physicists. We want to understand nature. Theoretical. How do you know that your theory is correct?
Well, it doesn't need to be, but maybe the calculations may be close a little bit. I mean, the results due to the experiments are close, so it gives me a sense, it gives me something there.
So how do you quantify it? It gives you a sense, but if you have the theory, who tells you that the theory is correct? Maybe the theory is wrong. Maybe the theory has been proven correct in 1 million previous measurements, but maybe you have just found a measurement which will tell you that the theory is wrong. The textbook, well, the nature doesn't come with a textbook.
I think there are not real value in nature. It is all just prediction.
Well, the nature will have some real value, but how do you know that what you measure is that real value?
I think that the more we try to measure it again and again, we get a average result that we get usually. And when we measure, when we try a new device to measure something, if we're close to that average value, I think that it's pretty accurate.
Well, what you are actually saying is, if the measurement is precise, then it is accurate, right? Well, because the more and more you make the same measurement.
I'm not actually saying that. What I'm saying is that what I'm saying that we're trying a new device to measure something.
Okay.
And we can say that it's accurate if it is close to what we're used to seeing in the other one.
So you're saying that have at least two groups measure the same thing with different means in a quite precise way, then it's accurate.
Yeah, I mean, it's like...
Well, in fact, that is the definition that we are using. There's no way to know that a measurement is really actually accurate, except then if it is a definition. Now, we will see how to define certain things in a moment. But you cannot really know if your measurement is accurate. If there are lots of different people, that's why the physics have to be repeatable. If different groups measure the same thing with different instruments at different places, in that case, and if they all agree on the measured value, then you can believe, it's a belief, it's not a proof, it's believed that it's accurate. Now, what are the definitions we have? These are the things that we define. Now, in this semester, we will be interested in the length. So what is 1 meter? You will say, okay, we take a ruler and measure it. But how do you know that the ruler that you use will be the same as the ruler that somebody else uses in the other part of the world or the other part of the universe? How do you define the meter? In fact, this is the definition of the meter that we use. It's the length that light travels in this much seconds. That is the definition of the length. That's the definition of 1 meter. True. Length that light travels in this much seconds in empty space. Okay, I should correct it. That is the definition of the meter. And okay, then it's this much seconds, but then what is a second? How do we define the second? Okay, you have all watches and they just tick, but again, how do we trust that everybody uses the same second? How can we make a definition of the second that everybody can use? And this is the definition. This is the time required for a particular atom, for a particular radiation for this much period. So if you count the periods of this radiation, if you count this much periods, that is 1 second. This is what the atomic clocks that use. They just count these periods. And the speed of light, it's a velocity. We don't measure it. We define it. It is exact. So since it's a definition, there's no error bars in the definition of the speed of light. It is exactly this number. Now the error bars here is in 1 meter, because 1 meter is something that we measure using light. 1 second is also something that we measure using light. So these quantities, so if you tell me that something has lasted for 1 second, there is an error bar over there because of the presence of use of the second. Now, why light, but not something else? Well, light has this, yes. It's as far as we know, it's constant for everybody. So, for example, now I look at your friend, he's just sleeping at 0 velocity. And if I'm moving, he's sleeping with minus, let's say, 1 meters per second in that direction. So his velocity changes if I start moving. But light, even if I move at 99% that speed in the same direction of the light, I will still measure its speed to be exactly this value. So wherever you go, or even you don't have to go, you just call your friend and tell them, okay, just measure this much oscillations of the cesium atom, and that will be 1 second. So we will all agree what 1 second is. And if we come together, compare our definitions of the second, they will agree, perfectly agree. Now we still have a problem over here. What's 1 kilogram? We don't have such a fundamental definition of a kilogram yet. And the way we define the kilogram is just, well, this would be in Paris, yes. There is a cylinder and we just call that 1 kilogram. Then of course there is a problem. How does a lab, let's say, to measure 1 kilogram? How do we know that if, we make a measurement and we say that, okay, the mass of this thing is 1 kilogram, how can we be sure that it is 1 kilogram? Now, we will be discussing mass in more detail, and what we do in the mass is we can just compare masses. We know means of comparing the masses. So, I think more or less every country, they just come together in fixed intervals. They go to Paris. Every country has this standard kilogram. They go there. They compare the masses with this standard kilogram over there. And they make sure that their national standard kilogram is 1 kilogram, and they have to calibrate all the measuring devices in the laboratories. Well, if you go to a supermarket and want to buy 1 kilogram of apples, I mean, whether it is so precise or not, whether it's accurate or not, it won't be so important. But if you are actually doing physics experiments where you want to be really, really precise, any deviation in the definition of the kilogram would be really important. And these are the fundamental units that we will be using throughout the semester. The kilogram, the meter, and the second. Okay, so this is what we did. Okay, so no, I will not continue. So I think do you have any questions before we go?
So you said about the probability. When something happens, for example, the event of problems. So if it happened, that means that there is like such kind of a reason which we were not aware of it before that happened, and when that happened, we can measure it, or we can do physics.
Not really.
So what the reason.
Okay, wait until you are third year. Or come to me after the class. Other questions? Okay, so see you on Thursday.